Okay. I have several commands before starting talking to you. So first one is a comment about the lecture video and the post-lecture slide. Okay. So lecture video will be posted in YouTube site, and the password is my name, BYUNGCHOCHOI. There are many videos, but this one is the one you should study. Okay? So it has titled with the name of this lecture and something, lecture 01, lecture 02. So today's video will be posted there, but sometime next week we move everything to the eeclassroom.org. Okay? So this is the last week, this last day for using the YouTube, and post-lecture is posted in LMS site. Okay? So after this week, probably we'll be using the eClassroom site also for the posting the video and the post-lecture slide. So everything is set up, and starting from next week, we'll go back to the normal schedule and the normal procedure. And another thing is about the lecture note. So I posted 3 things. One is part 1 of lecture slide, which contains the 200 something lecture slide for the former part of the lecture, and the part 2 contains 300 something lecture slide for the later part of this lecture. My original plan or my original goal was very aggressive. I want this class to be very intensive and comprehensive. Okay? So I hope this one is wide in scope and deep in the technical content, but I thought that might be too much, too aggressive. So, and the two goals are contradicting each other. Okay? So probably, but I want to deliver the complete knowledge about this topic, so you don't have repeat this study anymore. So I decided to go slowly. Okay? Try to convey to the older knowledge I think necessary for you. So as I said, some of you are not fully exposed to power electronics. So some of you might be very familiar with these things. So some students may feel boring. Okay, but be patient with me. So we'll move slowly, relatively slowly in the beginning, and we'll go speed up a little bit, step by step. So in the beginning, I think we need to move very slowly. Okay, so maybe we cannot finish 2 sets of lecture slides. Maybe we can finish 1, definitely, and plus some part of the part 2. Okay, so maybe we are not standing in the middle of something, but the original goal was too aggressive, so we stop and we resume the remaining part in the next semester, something like that. Okay, all right. Okay, that's one thing. Okay, and another thing was the comment about the YouTube and LMS site and my homepage eClassroom. Use of that. Okay. I'd like to go back several pages back. We covered this, and this explains the structure of Bach converter. So Bach this means step down sometimes. In old English, they said that Bach means stepping down something. Voltage in transformer technology is term borrowed from the transformer electrical engineering part. Okay. So Bach means stepping down voltage using this and generating another level of this voltage, and that is we went through the ideal DC to DC step down operation, and this is the practical one. So this part functions as the SPDT switch, and this is second order low pass filter, far less than ideal. Previously, in the ideal situation, we used ideal low pass filter transformer, which is not existing. All right. So we use this second order low pass filter, and with this set of two switches and this voltage source generate this pulse waveform from one fixed voltage, and simply this low pass filter is just generating the average value of this. Okay. In principle, this buck converter is extremely simple. Just this pulse waveform followed by low pass filter. That is the basic structure of buck converter. And we evaluate this transfer function from here to there to calculate the current attenuation. Attenuation of this ripple component. So this contains the DC component, and it also contains the harmonics. So this component will pass untouched, and we want to remove all the harmonic component, but that is impossible with this practical low pass filter. So we went through this slide. This shows the frequency responsive second order system. This x-axis is the frequency. Okay, so this is linear scale, and this is the linear scale, and inside of 1 decade you have log scale. This scale is called semi-log scale. It is a combination of linear scale and log scale, and this y-axis shown here is ratio of magnitude of our voltage divided by input voltage, which is Vx magnitude, evaluate in dB scale to any log scale. So this omega naught is double pole frequency of this practical second order low pass filter. If this filter is ideal low pass filter, it looks like this. This characteristic has this brick wall type, this curve like this. Okay. So this ideal filter is passing only the frequency component below omega naught. Okay. So this is in previous terminal loads. This is omega C of this low pass filter. But this is ideal low pass filter characteristics, and this is the characteristic of practical low pass filter. Okay. So I added this in previous lecture slide, and in the previous class I didn't show this, so I load this at home, right? So this is expression of Vxt, which is input of this low pass filter. This is described in terms of a Fourier series. So C dot is average component, DC component of this pulse waveforms. And this is the harmonics. If n is 1, there is the fundamental frequency component. If n is 2, there is the second harmonic. Okay? So, and output of this filter, VOT, this is the frequency domain things, and this is time domain expression. And the DC component is passing, untouched, does not change. So C naught remain the same, and the Cn becomes Cn prime, which is attenuated by this low pass filter. So let's assume the switching frequency is 100 times this double pole frequency of practical low pass filter, right? So n is 1. So just consider the fundamental component. So this is minus 40 dB per decade. This is the implication of the minus 2. So this is very long, as very, very inconvenient to use. So we are using this simple notation, minus 2. Then when n is 1, so this is decaying with this slope. So n is 1, this omega s is separated by 100 times. Okay, so we have this slope minus 40 dB per decade, and this is ratio in linear scale, which is 100. Because of this, then this number is minus 80 dB. So at this frequency, we have this attenuation of minus 80 dB. Okay, so this is the log scale. We need to change this to the linear scale to have some number. So C1 prime, which is the version of the coefficient of first fundamental component in linear scale, is C1 times this. Okay, this is conversion from this dB scale to the linear scale, which is this. Okay, so attenuation factor is this 10 to the minus 4. Right? This is obvious. Okay, for the second harmonics, we need to use number 2, and we have same thing, and this omega here, 2 times omega s is coming, so we have 200 here, then this one is minus 92, and if this is converted to the linear scale, we have this number. This is the attenuation factor. Right? This is a very simple thing, very simple algebra. So this is the thing I want to show to clarify the meaning of this. Okay? And this is the general expression. So Vxt is this one, then Vot output of this is this one, and this is a DC component. So everything combined in this is the infinite series of sinusoidal functions. Collectively, they are called as ripple component. So there are so many components in here. Right? So from these two things are obvious. If n goes to infinity, this attenuation goes to negative infinity, and this goes to 0. Okay, that's one thing. If there is a huge separation, this omega naught and omega s, and this will go converge to the 0 rapidly. Right? And this Cn is given by this. Some guy derived this, and you can go to your book table, so you can find this expression in the table. And we did actual calculation here using this example. This is one typical example of a converter. So with these parameters, we calculate the omega naught and the switching frequency is here. So 1 over this one is the switching frequency is 50 hertz in terms of radian per sec. We have this number, and the duty ratio is this one, 5 microsec divided by this 20 microsec is this number, and output of this converter is this input voltage times this duty ratio is 4. Okay, so this is the sketch of our voltage. So the value of output that will be 4, and we have some AC component here. Okay, so to evaluate the AC component or ripple component, we did some calculation. So we evaluate actually C1 prime, C2 prime, C3 prime, and C naught is DC component, which is passing freely, okay, without any attenuation. So this is the DC output of our voltage, and this everything here is attenuation factor, and that's plugging those numbers. We calculate this one. So this is the coefficient of fundamental component of our voltage. This is the second harmonic, third harmonic, so on. Right? So one observation here is this C naught, this component is 10 times larger than this, and it becomes more larger than this one. So the output voltage is actually practically 4 volt. Okay? And another one is C1 prime is compared with other coefficient of higher order harmonics. C1 is much larger. C1 prime is dominant term here. Okay? So when calculating this ripple component, you may ignore this one. They are so small. Then we consider this is the sinusoidal wave of fundamental frequency component. Then we have this expression. This is omega st, and this phi 1 is some angle. So we don't need to know. Okay? We don't care about this, the phase, just the magnitude is important. Then this is a sinusoidal waveform, and this is from here to there is C1 prime. So this variation is 2 times C1 prime. So in this case, This C1 prime is this number, and multiplication of 2 gives this number. This is the magnitude ripple component. This is very exact piece-wise workhead simulation, and comparing this and this, you can conclude this is excellent estimation here, right? And at the final part of this lecture, I emphasized that so any configuration combined with this SPDT switch and any type of low-pass filter, they form the Buck converter. So this is the standard second-order filter, low-pass filter, but there are other choices. This one is first-order filter. This is first-order LR filter. This is the standard second-order LCR filter. And here we have this filter followed by another stage of filter. This two-stage filter. Okay, and this is a comparison of this filter transfer function. This is the ratio of VO divided by Vx in terms of dB scale. Okay, so this is corner frequency, pole frequency. This is the pole frequency for this first order filter. This is the pole frequency of the second order filter, right? So this with first order filter, you have this kind of attenuation, and slope is -1, means -20 dB per decade. And with this one second order filter, we will have -2 slope, which means -40 dB per decade. And with this two-stage second order filter, you have first double pole here, but because of this stage, you have another double pole here. Okay? We separate this part and this part, so this is possible. This is a very good approximation because the combination of this and the combination of this is very different. Okay? The resonance frequency pole frequency of these two things, and this thing is far apart. Okay? So we can recognize this transfer function has another pole, another double pole here. Okay? So for this is the duty ratio is 0.5. This case duty ratio is 20 times 10 to -6 in the numerator, in the denominator, and in the numerator 10 times 10 to -6 times input voltage is 6. First one is 0.5, so output is 3 volt in this case. Okay, so and attenuation factor is this, and the switching frequency is this one. So the switching frequency is 50 kilohertz, 1 over this one. This is the switching period. 1 over switching period is switching frequency. So 50 kilohertz is 10 kilohertz, 20, 30, 40, 50. So take a look at this. Okay, and at this for this low pass filter, you have this much of attenuation. Probably it is 40 dB. I don't know. And this one has this much of attenuation, and lastly, this one has this much of attenuation. Right? So there are the waveforms of voltage for 3 different cases. This one is the first one. With this first order filter, the ripple is triangular waveforms. Okay, I'll explain this later in detail why we have triangular waveforms for this case. There is absence of capacitor. So capacitor is not there. So because of that, we have this triangular waveforms. So this average value is 3, but this ripple component is very huge. Okay? And this is this case, second order filter. So this 3 volt is somewhere here, and this is the ripple magnitude for this case. Okay? And lastly, with this two-stage filter, this ripple component is almost negligible. We have very ideal attenuation for the harmonic component, and it's almost ripple free. Okay, so this is excellent. But we use two-stage filter, so we use two passive components to filter out the DC component, attenuating the higher harmonics. Okay, but we spend extra element. But if you add these things, if you add this one, then use one of this, which is sum of two things. So which is this one, this plus, and this plus. All right. Then maybe you use the larger inductor, larger capacitor, and with that you build this second order low pass filter. Then characteristic of that is far less than this. Okay. So splitting into two stages is very good idea because almost the same filter size, and this plus this is about the same, and this plus this is about the same. Okay, you have a 10% increase in inductance and capacitance, but benefit of that is huge, right? So if you really want to remove the AC component, use multi-stage filter, right? So this is one potential configuration, but better configuration is you swap the position of this and this, and position of this and this. This is far better than previous one. Why is that? If this comes here later, okay, let me show this. So suppose you change your configuration like this. The smaller one is coming front. This is the same number. And larger one is coming later. Then this will remain the same. Okay? The position of this filter, position of this component, and the location of this double pole frequency is totally independent. Okay? Because this one is coming in front, this is coming in front, that is not true. Two entirely different things. If you analyze this circuit, you have same transfer function and the same body flow. So you have same attenuation spec. Then what is the good thing about this? We are assuming this resistive load, then that benefit is not apparent. But suppose this is some capacitive load. Okay? You have some board. You built some board, and you want to connect your board to the power supply. The first thing you will do is you put some capacitor in front of that to stabilize the voltage. So most of the case the load is capacitive. So almost all people, they put some capacitor. If you put small capacitor, smaller than capacitor, that is combined with this, and this additional capacitor is absorbed this. Its impact is very small. This inductance is the same. Okay, maybe you have a long wire, then there is additional inductor, and they are connected in series. This will affect the performance of this filter when this converter, this filter is connected to the inductive load. Most of the case, your load is inductive or capacitive or a combination of them or something else, very complicated. Nobody is using this resistor. This is for the experimental purpose in your laboratory. And the simulation purpose to study the principle of buck converter. So in practice, there is no resistive load. Okay? So for that case, just swapping this position will provide a lot of benefit in practical application. Okay? Right? So this is one practical things you need to know in practice. Okay, so in terms of circuit analysis, they are the same, right? But in terms of the performance with capacitive and inductive load, they are very different. Okay, so this is one example. And I'd like to explain the same, the very basic principle of analyzing this buck converter or any PWM converter or any switching circuit. Switching circuit means there are switches and the status of switch is changing all the time, periodically. That is called the switching circuit. This is a buck converter example. So when switch is connected, this is a reverse bias. So that configuration is this one. So this diode is turned off. So I'll be using this. Diode is turned off. And this is reduced to this. This is the on-time sub-circuit. This is called for the on-time sub-circuit, called as on-time sub-circuit, which is effective during this time period. The reason for this name is so obvious. When switch is turned on, this becomes linear circuit. This is a linear circuit, nothing is changing. If you take a look at only this circuit, it's a linear time invariant circuit. But you have another linear time invariant circuit. When this switch is turned off, there is an inductor current developed during this time, and the current want to keep continuity. There is no road to go, and that current is turning on this diode and create a path. This path is called the freewheeling path, and this diode is called the freewheeling diode. So you have this another circuit structure which is effective during this period. When switch is turned off, you will have this. Okay. So this circuit is time variant system, maybe nonlinear system as well, because the structure is periodically changing. That's called the time variant system, which is one type of nonlinear circuit. Okay. So thinking this is very complicated, very complex, or inconvenient, or maybe stupid. So smart people will decompose these two different things. One is this one. This is a linear time invariant circuit. This is another linear time invariant circuit. So you study characteristics of this, and you study characteristics of this individually, and later on you put them together in terms of their circuit behavior. Somehow you connect them, and you have some understanding or comprehension about the overall behavior of this circuit, original circuit, which is buck converter. That might be very natural way of analyzing this. Okay? So this is something very natural. So nobody wants to think everything all together. So it's separated into several sub-circuits. So this is called the piecewise linear circuit. You have two pieces of circuit, but each circuit is a linear circuit. So you can use all the conventional linear circuit analysis. You have learned the network analysis, circuit analysis course. So that content is written down here. The same thing. I already explained this, and this is when switch turned on. This will be this one, and this will be this one. Okay. So try to understand the startup behavior of a converter using this concept. Okay. Startup means you have this buck converter. Initially, inductor current is 0. Capacitor voltage is also 0. So there is no energy storage in the L and C. Okay. From that, this converter is starting operation by switching this one periodically. Okay. Their response is called startup response. So I have drawn the startup response here. So this is on-time sub-circuit, and this off-time sub-circuit during the startup process circuit present this one, this one, this one, this one all the time repeatedly, and one part of this and the other part of this. Okay, continuing that, right? Okay, there is a capacitor and there is an inductor. So this inductor is a very critical component for the operation of buck converter. Without inductor, there is no buck converter. So we have inductor, and inductor voltage, this part is Vs. This is Vs, and the output of this voltage Vs, and this voltage is Vo. Initially, this one might be 0. Okay, because no energy content is existing in this capacitor. So this voltage is initially 0. So for that case, Vs is larger than V0. This is a fixed value. This is 0. So obviously this one is true, and this one is true in general, because output of this voltage is always lower than this, because the duty ratio is some number less than 1. Duty ratio is some number less than 1. The output voltage is always smaller than this. So this condition is always valid. That means voltage across VL is Vs minus Vo is always larger than 0. It's positive. Okay? So basic inductor equation, when inductor is connected to some DC voltage, then this is VL, then VL divided by T is slope of current increase, and the current is linearly increasing. This is one expression of voltage current circuit equation of an inductor, but this one is most important. Always we are exciting this inductor as a DC voltage source. Always the DC voltage is connected to the inductor. Okay, according to your knowledge of network of the sophomore course, inductor behaves as a short circuit in DC. So maybe you may wonder what happened to the circuit. Circuit is shorted. We are in trouble. Not at all. That is not the case. Okay. So there is a DC across the inductor. Then inductor current is simply increasing linearly with this slope. So in this on-time period, inductor current is increasing. So it starts from 0 and inductor current is increasing. That means the energy stored here is increasing. That means energy is transferred from source to the inductor. So during on-time period, energy transfer will occur from source to the inductor. Right? So that is this part. So inductor current is increasing because this voltage is positive, and this is turned off. Then we have this uptime circuit. Then inductor voltage is voltage across this inductor. VL is this voltage is 0, right? 0 minus this voltage is larger than 0. VO is VL is always negative, less than 0, means inductor current is always decreasing during this part. What will happen here? During on-time period in which the inductor current is increasing, the energy is transferred to this inductor, and at this time, the stored energy is transferred to the load because current is decreasing. This is negative, inductor voltage negative. Then ILT, this is slope is decreasing. So inductor current is decreasing. Okay. So this is energy transfer from source to the inductor. This is energy release. Okay. Energy is released from the inductor and transferred to the load. So, okay. This is the beginning part of this startup process. So during this startup process, transferred energy is larger than energy released to the load. Okay. So this is increased much, and this is increased small. So transferred energy is released to the load. Okay. Extra energy is stored here. So this keep on increasing in this fashion. All right. And it goes like this, and eventually this will settle into this triangular waveforms. This slope is the same as this slope. Means energy transferred to the inductor is same as energy released from the inductor to load. That is the steady state. Then this average value will remain the same. Okay. That means some finite energy corresponding to the value of this current is stored in this inductor, and this part, thus additional energy is coming in, and at this part, at this period, that additional energy is released to the load, okay, in this manner. So this is a steady state, and at this state, the transferred energy is same as the released energy. So we reach the steady state. Okay, so the reaching the steady state is explained using this simple piecewise linear circuit analysis. So this is one simple example of using piecewise linear analysis. But we are using this analysis idea all the time. Okay. One thing here is this average value of inductor current in the steady state is the steady state out voltage divided by load resistor R. This is R, then this IL, average value of this triangular type inductor current is VO divided by R. Okay, so we will prove this in the next slide. Try to understand this. Okay, then if inductor is designed properly, okay, you made correct connections, then eventually you have this state. This is steady state. Okay, so this value is the same as this value. This peak value of inductor current is same as the next peak value. So everything is periodic. This is called steady state. All right. So why we have this condition? The steady state value of this inductor current is given by this. Okay. Very easy. So let me explain this. Okay. This is another maybe about the same converter. So here the switching period is this one, and Joule ratio is this, and then output voltage is this times this number is 4 volt. So our voltage is VO 16 times 4 volt, and this IO is this voltage is 4 volt, and we have 0.1 resistor. Previously the resistor was 1, but for some reason I decreased this a lot. Then this IO, the current lossing into the load is VO divided by R is 4 divided by 0.1 is 40 amp. Okay. That value is same as average value of this inductor current. Why is that? Okay, this is point A, and the setup at point A, then ILT, not equal sign, is same as ICT plus IO, right? So this is obvious. Okay. So this is the equation for the instantaneous waveforms, but you take average value of them. So you put bar here, you put bar here. Okay. The average value of this capacitor current should be 0. Okay, I'll explain it that later. Okay, with a simple example. So for all the practical converters, average value of this is 0. Okay, then this is 0. This KCL holds for the instantaneous waveform, and this should hold in the average version of this. And IO is already this DC, and this is 0. Okay. The average value of capacitor current should be 0. Then this is the same as this. So that is written here. IO is this one, and IL average, IC average is this one, and this middle term is 0. And because of that, we have this behavior, right? So which is this one, and this is the simulation waveforms of inductor current of this, and this final value, average value of this inductor current is gonna be 40 amp. Okay? So you understand it. Okay? I mentioned the PSIM and the PSIM program. PSIM is software, name of the software. That is include the attached file. PSIM zip file is the execution file for this software. So if you learn that program, that the student version of the PSIM will be stored in your computer, then you can perform this using this. Okay, this is the file name. So there is separate by chapter 1, 2, something like that. Then look for this file. Then you see this. Okay, everything is graphic. Okay, I don't like PSIM very much, but the best part of PSIM is very easy to use and very convenient to use in teaching, right? Because this is just schematic, and this is also the model of the PSIM file. And just clicking this, there are some buttons. Then clicking some button, I will show you the execution of this maybe next week sometime through this video. I'll take video separately, and I learn video through this, and I'll explain some important things. But everything is so easy. Okay, if you click some button once, then you can know everything about the click. Most of the things. There is the help command. You click that, you push that. There is a very kind the explanation of that function. Okay, and anyway, this is for converter. So this is a MOSFET switch. You are using MOSFET switch all the time, and this is the switch, drain, source, gate, and this diode is built-in diode. If you have MOSFET, then there is a diode. They come all together as a pair. Okay, you cannot make without this capacitor for this MOSFET for the practical reason. If you avoid this the performance of this MOSFET is very poor. You cannot use in practice. So to make this thing applicable, usable for the practical purpose, we do something during that process. This diode is created unintentionally. This is the byproduct, so they come all together. So this is called anti-parallel body diode. The name for that is because the usually current is flowing through the drain to source, this current flow direction, and this diode is opposite to that direction. So this diode is reverse biased all the time for the PWM converter. So this diode is nothing, okay, not doing anything, but there is a diode. Okay, some case you should consider this, or sometimes you make use of it. You exploit the presence of this plastic diode, body diode. Some case, some special case, but the most case you ignore this. They are reverse biased, not existing. But in PSIM, they come all together. Diode and this inductor and capacitor. This is resistor. This is the probe. This is like the current probe. So this is current display. This has some gain, and the inductor current is connected to here, just 1-to-1 fashion. The gain might be 1 here, okay? And this is the scope, something like this, and it's connected here. Then our voltage will be displayed here, okay? Maybe you don't need this, okay? This is buffer, but you directly connect this to here, then you will see this, okay? With this, you click this, you will see this screen. This screen, okay? First, you click this, you will see the out voltage. So this is 0, and the division of this is 2 volt per division. So it start out from the 0 and go to the 4 volt for this case. And this load current it goes like this as we covered, and eventually this is 10 volt, 20 volt, 30 volt, 40 volt, okay, like this, okay. And let me explain this. This is important. You will be using this a lot, okay. This is the power stage. You need some drive signal of this MOSFET. This is the drive signal for the MOSFET. And you have this. This is RS flip-flop. And this is what? This is comparator. This is operational amplifier. And comparator and operational amplifier, they use same symbol, but they are different. Right? You can use, this is OPM, it is a very general device. Using OPM, you can make comparator, but you cannot make OPM using this comparator. So this comparator is kind of OPM, operational amplifier, specially configured to have good comparator characteristics. This is customized for the comparator, called comparator. Device is called comparator, but so it cannot be used as the general OPM. And conversely, this OPM can be configured like this. Very easy. Just forget about this. Use these two terminals. That becomes as the comparator. Okay. So, and this is what? This, if you connect this voltage and this two port is virtually connected, then that input voltage is same as this out voltage. This is unit gain buffer. So this is the unit buffer. Voltage buffer, actually. Voltage buffer, okay? And this is a combination of this RS flip-flop and this comparator works as a PWM block. This will generate PWM signal, PWM block. Okay, so even they use the same symbol, OPM is different from comparator. This is rather important. In the past, one of my students, PhD student, he confused with this, okay, and everything screwed up there. All right, so we have a comparator, and comparator is connected to this signal, and this is lamp signal. Lamp signal is something like this. It increase this and decrease abruptly, like this. Sawtooth waveforms is generated here. So this 3.8 is peak value of this waveform. This is called the lamp waveform or sawtooth waveform. That's different from the triangular waveforms. Okay, and this is the pulse waveforms. So pulse is generated with short duration period like this. Okay, and they are synchronized with this. The beginning of the lamp is synchronized the leading edge of this lamp. Okay, these pulse waveforms, right? And the operation of this RS flop and combination of this with this, and this voltage is 0.95 is unit gain buffer. This is nothing. Same voltage is here. And this is 3.8, and this voltage is somewhere here, is 0.95, which is 1/4 of this. Okay, at the beginning, instant of this leading edge of this, or the instant of the ramping up of this signal, this becomes high. Okay, so this is Q switch drive signal becomes large at this moment, and this voltage and this voltage is compared here, then if they cross each other, this output will be changed. Because of this RS flip-flop, then off signal is generated. It goes like this, and on time is generated, and off time is generated, something like that. Okay. Then this, suppose this is 20 microsec. Then this on-time period is what? Is 5 microsec. Okay? Because the ratio between this is 4. Okay? So 4 times of this is this number. So ratio between this to this is same as ratio between this value and this value, because of we are talking about two triangle in similar type. Okay, so this is the pulse waveforms. Okay, and then output voltage of this should be what? This 16 times 4. Right? So this is a PWM block, and with this is the open loop operation of this converter. Open loop means usually output is connected to here by some means. Okay, that is a closed loop control. There is a loop, no loop between this out voltage and this PWM block. Is open loop operation of this. Okay, suppose you need to simulate some converter with duration of 0.5, then you increase this number twice. Then you have the converter of duration 0.5. This is very handy. Okay, this is handy for the simulation, and this is the handy for the hardware implementation. Okay. So later on, you start this. You study this and try to simulate this with some modification. Okay, this is the simplest possible case of simulation, right? And it starts from 0. It looks like the scope, the screen of oscilloscope waveform is increasing gradually. You can watch the evolution of the waveforms, which is very good, right? We have several techniques. Circuit analysis technique will be using for the analysis of a converter or any other PWM converter or any other switching circuit. Of course, we use Ohm's law, device equation of inductor, capacitor, and transformer. We use the KCL, KVL, Kirchhoff's law. Okay, that's the basic things. And we have additional 4 items for us. Okay. First one is piecewise linear analysis. We already went through this. The operation of converter is analyzed by examining each sub-circuit individually and later correctly considering operation of 2 individual sub-circuits. Okay. We already did this. And this one is very important. Small ripple approximation is output of any converter always contains some ripple component, can be small, or some case can be large. But we assume that ripple is so small, the output is considered as a pure DC. Right? That is called the small ripple approximation. The ripple component in the converter output is so small that our voltage can be considered as pure DC. Right? So very easy to use and very easy to remember, okay, and understand. Why this is still useful? As I said, in the output of converter, there is always AC ripple. So for the exact circuit analysis, you should consider all the ripple components to have exact expression for the out voltage. That is useless. Okay, that is a job for the computers. Not you. Human has brain. That stupid job is for the brainless machines, computers. Okay. We assume everything is DC output. No, not everything. Output is DC, and we have some solutions. Okay. The justification for this is at this there are 2 aspects. Okay. One is everyone is trying to reduce the ripple component. So they are using large capacitor to reduce ripple. They use 2-stage output filter to reduce ripple. So ripple is actually for the practical application, it's so small, can be ignored. The impact of ripple on the circuit operation is nearly negligible, can be ignored. Okay, there is no loss of information analysis, just using DC. For the out voltage, it simplifies analysis So it provides streamlined analysis, quick and easy. Okay, that's one thing. Okay, more important thing is, suppose you want to have the exact amount of the ripple component. Okay, then you use the solution of with this using the small ripple approximation. Consider output as a pure DC, and you find the you perform the simplified analysis, streamlined analysis, and get the result. And from that result, actual magnitude of ripple component is always reconstructed, if you want, with extremely good accuracy. Okay, so you are losing nothing. Okay, if you want to know, then you can know from the simple formula. Okay, so by doing this, you are losing nothing. Right? So two things. Another one is volt-second balance condition. This means inductor voltage applied in the inductor over one switching period should be 0. That means there is inductor, DC voltage is applied, positive DC voltage applied, then negative voltage should applied at the same period in the same amount. That is this volt-second balance condition. Okay. So for the inductor voltage, we are applying always DC. So DC value is this. Okay. Then this area of this and area of this VL should be the same for one switching period. Okay. Otherwise, what will happen? If this is not met, this is slightly larger than this one in terms of their area, then inductor will be saturated. Okay, you know what inductor saturation is. Upon the saturation, inductance of inductor suddenly becomes 0. Then there is just a tragic accident, catastrophic accident will occur, and your circuit will be destroyed. All right? But the circuit you are dealing with is practical one. That kind of disaster won't happen. So in the converter circuit is designed in the way this inductor voltage meet the volt-second balance condition. Okay, so you can use this as a circuit theorem. If there is an inductor in your switching circuit, the average value of voltage is 0, meaning this. Okay, this one area of this should be the same as this. Okay, that means so in the one switching period, they balanced out to 0. Then the integer multiples of switching period should be 0. But in general, for long period, okay, you add them up. In the final period, there is some unbalance, but unbalance is so small. Okay, compared to this long period of this summation. So in general, without mentioning anything, voltage, magnitude, or the timing information, you assume the average value of inductor voltage is always 0. Okay, average value of that. This is the volt-second balance condition. For the capacitor, there is M-second balance condition. Means if you have a capacitor, you are driving capacitor, always driving capacitor with current, constant current, something like this. This is a positive current flowing through the capacitor, this time period. This is negative current. Then area of this should be same as area of this. Always same as this. Why is that? What happened? It does not comply with this requirement. Capacitor voltage will be increased slightly, continually until it exceeds the voltage rating of your capacitor, and the capacitor will explode. Everything will be gone. Okay? To avoid that tragic situation, your converter circuit is designed, prepared. All the capacitor can meet this M-second balance condition, namely the average value of capacitor current over one switching period is 0, over integer multiples of switching period is 0, average value of the 0 in general, regardless of operational period. Okay? So this is very important. So there are this additional circuit analysis technique you should make use of this. You should exploit these characteristics. This is good for you. Okay, you need to use these things for the circuit analysis. Okay. Buck converter in steady state. Right? Assume we have buck converter and it went through the startup process and it reached steady state, and this is our voltage. So our voltage is constant with the assumption, with the small approximation, and this value is already known. This is duty ratio times Vs. Okay, so this is pure DC, and we know value of this already. And when switch is connected, the current path will be like this. Switch is connected, then diode is turned off. So this current path is for DTS. DTS is what? This is on time period. Okay, and uptime period. This is turned off. During on-time period, diode is turned off by this voltage, and during uptime period, switch is turned off. Then current path is formed following this path. Okay, this is for 1 minus DTS. So with this, you have this circuit. So there is a voltage source and inductor. This is connected, and diode is open. So is directly connected. We have L, R, our voltage, which is this one. This is on-time sub-circuit. It reduces this. Okay. During the uptime period, switch is turned off, and diode is conducting. So there is a diode conducting. This with this colored one, there is a diode is connected, is shorted. So we have this circuit. Actually, this is named as on-time sub-circuit. This is named as uptime sub-circuit. Okay. And waveform of this, voltage waveform of this is switch drive signal, conceptual switch drive signal, DTS, 1 minus DTS, on-time period, uptime period. Voltage across this is Vs minus Vo. And voltage across this diode during this period is, this is negative, minus Vo. And according to the volt-second balance condition, this area should be the same. Otherwise, your converter won't reach steady state. So when you are talking about steady state, this condition is met. That means area of this is the same as area of B. Right? This is a volt-second balance condition. Okay, so this is the expression for the volt-second balance condition. This is area of this. Value is this one, and this period. This is the value of this negative VO, but we are calculating area, and forget about minus sign. So you have area, and using this, you have this expression. So VO is given by D times Vs. We come up with this voltage gain expression from the time domain interpretation and the frequency domain interpretation and this steady state circuit analysis. Okay, so because this D is something between 0 and 1, so that means voltage gain start from 0 and upper limit is 1, so they are same thing. Okay, so this is buck converter. We are using piecewise linear analysis, and we are using volt-second balance condition. And let me explain just this first one, and later on we discuss remaining part next week. Okay, this is an inductor current waveform. We know that this average value of inductor is same as the load current. Because of the previous discussions, this average value is VO divided by R. Okay. Expression of inductor current is this one, for DC drive, when DC is applied across the inductor, this is a slope, this is a slope, and this is the time. So it linearly increasing. So it from here, some value, it linearly increasing like this. Okay. Why it's not increasing from 0? It has this fixed average value, so it should start from here, and during this time period, this should decrease, right? So compare with this, when this voltage positive, inductor current is increasing from this minimum value past the average value and reaches maximum value and decreases to the minimum value, and it is repeating this waveforms forever. This is what? This is triangular waveforms. So in the state, the inductor current is always triangular waveforms for this case, right? And we know this average value is given by this, and we know the slope of this, we know voltage across the inductor, each one is this, and divided by L is slope, and this is the T period of time is dts, so this is del IL. The increasement from here to there should be decreasement from here to there. To reach steady state, this value should be the same, and this value should be the same. Okay? So this must be true. Otherwise, you are not in the steady state, still in transient period, and then maximum value is this average value times after this variation, and the minimum value is average value minus after period. Okay? All right. We stop here, and we'll continue the remaining part. Okay? I think we're moving too slowly, but let's speed up. Okay? But this is very, very important for the beginners. Okay? All right. Okay.